Welcome to another video where we do understanding hypothesis test using simulations. And this time around we're going to look at the chi-square test for association. As always, I'm going to do my recording and all my work inside of a Google Colab notebook. And I'll show you just how to do that. As a reminder, if you go to your Google Drive and you click Next, you can see all the familiar things, Google Docs, Google Sheets. But if you come right down to the bottom, under More, you see Google Colab. Now, Google creates many apps. They don't list all of them. So if you don't see Google Colab, you can come down to Connect More Apps. And you can simply search for Colab in the search bar. And there we go. It's the first one on the list. You can just click and install it. I've already installed it, so it's there for me. It's very easy to do. And now all you have to do is save file, come to the new, I should say, go to More and click on Google Colab. Now, Colab is, as I mentioned, Google's version of Jupyter Notebooks, and it allows me to create code. And of course, when you open it, you see on the right-hand side, if you don't, just click on this big toggle Gemini button at the bottom, you see Gemini on the right-hand side. So you can interact with the chatbot right here and it'll write the code for you. And that's what we're going to do. For instance, if I come to this code cell here and I were to write a simple prompt, and there's my prompt. Remember, prompts always start with a little hashtag. So I can write a prompt there or down here, but I've written it right in the code cell and I said import the NumPy packages and the stats module from SciPy. If I click enter, look at that, the code gets written for me. All I have to do is to hit the tab key to accept that code, and that's legitimate Python code, and it's going to run, execute, and everything works very well. And that's what we do in this series. We get AI to write our code for us so that we can concentrate on understanding the statistics. And so we're back at our notebook, the chi-square test for association. Let's just talk a little bit about the introduction. This is going to be about understanding the chi-square test for association using the formal test itself. So we're just going to get Gemini to actually write the code and do the test for us. But we're also going to use simulations so that we understand, what this test is all about. So to remind you, the chi-square test for association that is used to test the claim, and remember, claim is always your alternative hypothesis, that there is an association between two categorical variables. As always, I start my notebooks with the Python packages. How do I do all of this? Just you may be wondering if you haven't seen this before. Remember, these are all just cells in a Google Notebook. And if I hover in between any two cells, you can see I can add a code cell or a text cell. And all of these cells up till now is just very simply these text cells. If I double click on them, they open for editing. And as you can see, the familiar things here, bold, italic, you can do a numbered list, bullet point list, you can add images, etc. The way that you control the size of the font is by hashtags. Now the hashtags, remember, in a text cell controls the size of the font, whereas in a code cell, it allows you to write a prompt to the large language model. So there we go. I've put two hashtags, so that makes it slightly smaller font than the biggest font, which I used right at the top here. Let's have a quick look at that. See a single hashtag there. That's the biggest font, so I'm going to reserve that for my title, and everything else is a subtitle or a subtitle, etc. Back to the Python packages though, I'm going to set up this notebook. I want to use NumPy for my numerical computation. I want to use the stats module from SciPy for my statistical computing. I want to use the pyplot module from matplotlib for my plotting. And I want to set the notebook to generate high resolution plots. Yes, you do need a little bit of understanding of Python to know that Python is a core language, but you can extend the language by importing some packages or modules inside of those packages. And that's just what I've done. Now, if you do any kind of research, you will know these are the packages that we use all the time. So very easy to become familiar with this. Now, I don't want you to watch me type in this series. So I've already done all the typing, but we can just investigate this. So this is the prompt, and you saw me do that in the previous section when I just opened a new notebook. That's all you type in a code cell. So remember, you hover in between, you hit the code cell, and you start with a hashtag in space, and you write your prompt. You press the return or enter key to go to the next line, and Gemini will write all the code for you. So throughout this video, do remember that you can just pause the video and you can inspect this prompt that I wrote. And you can write the same prompt yourself and you can look at the code that gets executed. Do remember, because this is Colab, I can go up to runtime, I can change the runtime type, and I can actually choose Python or R or Julia. but we're going to do everything in Python. And depending on the version that you have of Colab, you also have access, of course, to some of the hardware that Google provides. And you can even select a machine that's got high RAM. Remember, all of this is happening on computers at Google. You just see the results on your screen. This code does not get executed on your own computer. So there we go. I'm going to run this code cell, and I can click in it and hit Shift Return or Shift Enter, or I can just hit the little play button, and you see, first of all, it's going to connect to Google's computers. It's going to spin up a kernel of Python, and it's going to execute the Python on Google's side, and I'm going to see the results on this side. So I see my little check mark. Everything worked well. My next prompt was import the pyplot module from matplotlib, Shift and Enter, and that's going to execute. You see the little check mark there. And then finally, I'm going to set the inline backend to Retina using the %config magic command. That was my prompt. Again, you get used to that very, very quickly. And it wrote the code for me, %config, that's a magic command, inline backend.fig_format equals Retina, and that gives me a high resolution plot. So that's pretty standard for any research project in Python. We're going to import those packages, and we're going to create high resolution plots. Very easy to memorize, although I didn't have to write any of that code. I just wrote the prompts, but I still needed a little bit of knowledge of Python to be able to write those prompts. Let's be fair. So hypothesis test. Now we're going to have, for the chi-square test, for association, we need two categorical variables. Now they need not be binary, but binary meaning that each of the variables only has two possible outcomes. It's just the easiest one to explain, and so that's what I'm going to do. So I'm going to imagine that we have these two columns in our spreadsheet. One is going to be an exposure variable, the other one's going to be a disease variable, and each of them are going to have two sample space elements. So for the exposure, we're going to have either someone was exposed or they were not exposed. You can think about being vaccinated or not vaccinated, or smoking and not smoking, sort of any binary exposure. And then there's some disease, and some people have the disease, some people don't have the disease. So I want to generate some random data. And that's a very good thing to do, because remember, in any hypothesis test, we're going to have this null hypothesis, and that's going to say that there's randomness in the population. And we're going to distill that down to saying that there's no association between these two. And if I just generate random observations, what I'm saying is these two variables are not associated with each other. So what I want to do in generating this, I think it's worthwhile for us to have a look at the code. Remember, I'm just going to write these green bits. So I just write the prompt, and Gemini writes the code for me. But again, remember, just pause anyway. You can try and write the similar prompt and see what happens for you. I'm just going to go through it quickly. I said create a NumPy array that contains the sample space elements of the exposure variable and assign the array to the variable exposure_labels. I put those in little tick marks. I'm just trying to help Gemini out. When you put things in tick marks, it's generally seen as this is code. And so that's exactly what it wrote. So this piece of code here, that's what Gemini wrote. It created this variable exposure_labels and assigned to that, the single equal symbol is a sign, a NumPy array. And inside of the NumPy array, we see the two sample space elements as text or as strings, exposure and non-exposure. And I did the exact same thing for disease. So pause, have a look at it, think about it. It's quite simple. Now the next thing that I want to do is I want to return 300 random observations. So what I'm thinking of is that I have 300 subjects, but for each one of them, it's going to be randomly assigned to exposure, not exposure, and randomly assigned to either disease or no disease. And with that randomness, what I'm trying to simulate is that these two variables, exposure and disease, are totally independent from each other. And that's what I'm going to do with the code here. We can examine it a little bit. The first thing that I do is to say seed the pseudo-random number generator with the integer 12. Because your computer cannot really generate random values, so there's usually a deterministic algorithm. And that algorithm gets seeded by a number. Sometimes it's done by, well, that exact time that you hit the return or enter key. There's going to be a timestamp. And that timestamp with any 1 second, remember your computer can do megahertz, so many times per second, it can generate a little timestamp, and that will seed the pseudo-random number generator. There are other ways to go about it. But this time I'm forcing the the pseudo random number generator. We call it pseudo because it's not really random, it is an algorithm. But if I seed it with a number, it means every time I run this code, I'm going to get the exact same pseudo random values back. And if you run it, you're also going to get the same. And that's very nice when you do a tutorial or you teach, because we're all going to get the same random results. That's what that is about. Next one is I'm going to assign the sample space 300 to the variable n. So that's my prompt. And there's the code that was written, n equals 300. Then I said randomly sample n rows. So in my case, that would be 300 from the exposure labels and assign it to the variable random underscore exposure. Then I said randomly sample n rows from disease underscore labels and assign it to the variable random underscore disease. And then finally stack those two together. So what I'm trying to generate is just those two rows in a spreadsheet. And so let's run this code. And then what I'm going to do is just inspect the first 10 observations. So I said return the first 10 observations. The code was written for me. Data underscore array is where we save that. Right there. I said assign the results there to data array. And if I run this code, you can see, I'm just going to rerun it. You can already see the results there. So you should get exactly the same results. So this first person did not have exposure and they developed the disease. Same for the second person. The third person had the exposure and developed the disease. Next one, no exposure, no disease. You can see where this is going. There would be 4 unique combinations: exposure, disease, exposure, not disease, not exposure, disease, not exposure, no disease. And so I can create a contingency table from this data. And again, I'm going to now stop telling you about my prompt. You can pause and read the prompts yourself. But what I'm trying to generate now is a contingency table to tell me those 4 unique combinations, those joint frequencies, how much do I get? And I've run that code, and then I want to print it to the screen, and you can see it there, 78, 77, 76, 69. So those are the 4 joint frequencies, and that's what I use for a Pearson's chi-square test. And so there we have the test, the chi-square test for independence. We want to test the association between these 2 variables with a categorical level of measurement at the 5% level of significance. So our type 1 error rate, we are willing to reject the null hypothesis, and we're willing to be wrong 5% of the time by doing that rejection. So there's our hypotheses. The null hypothesis, the variables are not associated. The alternative hypothesis, the variables are associated. Now I want to calculate my test statistic. Now I'm going to call my test statistic x squared, and I'm saying x squared follows or is described by a chi-square distribution on given degrees of freedom under the null hypothesis. If that doesn't ring any bells, don't worry, the simulation is going to explain all of this for us. There's my equation for calculating this test statistic. It's a measure of how different those 4 values right here in my contingency table, that's my observed values, how different are they from what I would expect if the null hypothesis were true. So what we're going to calculate is our chi-squared statistic from our data, from that contingency table of 4 values, a p-value, what was the degrees of freedom, and then the table of expected values under the null hypothesis. And again, that's the prompt I wrote. That's the code I got. I'm going to execute that. And so let's look at the results. I'm going to return the test statistic and p-value. And you can see the test statistic is 0.0607922. And my p-value was quite large at 0.805. And you already know that if you get a p-value that is larger than your type 1 error rate or your alpha value, your level of significance, then we fail to reject the null hypothesis. So there we go. Our x-squared statistic was a very small 0.061 with a very large p-value of 0.805. I can also then get the degrees of freedom. So that was a very specific chi-square distribution on a single degree of freedom under the null hypothesis. And then I can also return the expected table. And so remember, our values up here were 78, 77, 76, 69. But if the null hypothesis were true, this is what I would expect out of my total of 300 observations: 79.567, 75.433, 74.433, and 70.567. That's what I would expect. And my x squared statistic is a measure of how different the observed frequencies were from these. I do have to have that these values are at least 5, and you can see all 4 of the expected values are at least 5. I'm happy to use the chi-squared test. So that might not make a lot of sense, so let's simulate some results, and you can see where all of this comes from. So to do that, I've got to do a couple of things, and you'll have to go with me on this. Pause the video, look at the code, look at the prompts I wrote, make sure you understand it. At a high level though, I want to generate a user-defined function. So I want to create a Python function that returns random observations as above. I created those 300 observations. I want to do the same thing, but I want to add a parameter called n, so that if I want 300 or 400 or 500 or 10 or 20, I can just change that value in. And that's the prompt I wrote there, and that generates a function for me that'll do exactly that, exactly what I did before. Other than that, I can now change the number in. That's up to me. So I want to test this user-defined function. And so I'm going to call that function, and I'm going to say let n be 10, so that we only get 10 values back. And that's exactly what I do there. And there you can see 10 observations. So the first person had exposure and then disease. The second one, not exposure, no disease, etc. It is just random. Now you are going to get back different values because I'm not seeding the pseudo-random number generator here. So every time I run this, I should get different results. And that's the point. The next user-defined function that I do is to get to this idea of the frequentist approach to statistics. So what I want to say is, well, do this for me. Randomly generate, say, 300 observations for me. Once you've done that, calculate an x-squared statistic for me. And do this over and over and over and over again so that I build up all these x-squared test statistics, so that I can eventually just create a histogram of all my x-squared statistics. And that's exactly what we're saying to each other in statistics. We're saying, let the null hypothesis be true. Let's randomly sample from such a population in which the null hypothesis holds. And I'm doing that by randomly assigning exposure and disease to each observation, each participant. So I'm trying to simulate the fact that these two are totally independent from each other. And then I say, well, sample from such a population. Calculate then my little contingency table, calculate an x-squared statistic, and let's do this over and over and over again such that I get many x-squared statistics under the null hypothesis. And then we are going to do something with all those x-squared statistics. So that is the next function that I'm generating. It's a user-defined function that will just do this repeatedly for me. I'm building in a special parameter called k, and that k there tells the program how many times should it repeat this process. Remember, we would want to simulate this data from an infinite population, and we want to do this repeats an infinite number of times. This is real life, so I cannot do that. And so I want to limit myself to k. That's the number of times I want this repeated, and n still is the number of participants that are selected each time. So that's what my function is about. I'm going to test this function now. I'm going to say select 150 observations, so generate 150 observations, and repeat this 10 times so that I get 10 chi-square values. And if I run that code, lo and behold, you see there is my 10 chi-square values. The first one was 0, the next one was 0.183. That's the point. I want to do this over and over again. That is the frequentist approach to statistics. And so the next thing that I'm going to do, I'm going to use these functions that I've just generated, and I'm going to say, well, select 300 observations, generate 300 random observations for me, calculate an x-squared statistic, and do that 20,000 times so that I get 20,000 x-squared values. It sounds like a lot, but it's really nothing. I should actually be doing this an infinite number of times, but of course, real life, I cannot do that. So that code's going to take a couple of seconds to execute, and then we are going to have 20,000 x-squared test statistics. But remember, I'm simulating this from a population in which these two variables are totally independent from each other because I did random assignment. So there we have. Now it's very difficult for computer to plot 20,000 data points. So what I'm going to do is just randomly select 400 of them. And that's what I'm doing here. And then I want to create a density histogram. And once I do that, this is exactly what I see. Look at that. Doesn't that remind you of something? It reminds you of a chi-square distribution, doesn't it? And look at it, it's in front of you, in front of your eyes. Look at that distribution. I would get the majority of values close to 0 because this is simulated from a population in which these two variables are really independent from each other. And as we get further away from 0, there is a drop in the density of these x-squared values. The further I get away from 0, I see fewer and fewer of them. In actual fact, what we can do is to calculate the 95th percentile. What is the 95th percentile of all these 20,000 x squared values? Well, it's the value for which 95% of values will be less than that value, and only 5% would be more. And you know what that is? That's our critical value. So let's calculate that, which is exactly what I've done, and we find a 95th percentile value of about 3.4, which means only 5% of those 20,000 x squared values are more than 3.4. That is a critical value for an alpha value of 0.05. I'm saying I want those extreme 5% of cases in my region of rejection. So yes, calculate the 95th percentile, and then only 5% of all those x squared values will be more than that value. And so there I got about 3.4. Now I can recreate my density histogram. And so again, please pause there. You can read that whole long prompt that I wrote to generate this plot. You can also I'll go slowly. You can pause there, look at the screen and see the code that was written. See if Gemini wrote the same code for you, but this is what we generated. So let's have a look at this. This is a density histogram of 400 of those random test statistics. I cannot plot all 20,000. And look at that on this red dotted line. That was my 95th percentile, which means every value larger than that, that's why it's our critical value, we're going to call this the region of rejection. If I find a x squared statistic in this region of rejection, then I'm happy to make a type 1 error. Because you are making a type 1 error, because all these x squareds, even the ones out here in the extreme, they were generated from a population in which the null hypothesis holds. And so if I reject a value out there, I am making a type 1 error. But we said beforehand, we are happy to do that. We are happy to be wrong. That's our type 1 error rate, or our level of significance. So our single test statistic was 0.061, and that is definitely not greater than the 3.4, the 95th percentile. So we failed to reject the null hypothesis. We did not get an x squared that was out here in the region of rejection. There is my prompt. I want to plot all of this, so you can pause and read that. There's my code. I'll pause every now and again so that you can pause the video and have a look at it yourself. And there is our simulation. Look, there's our test statistic. It's definitely amongst the 95% least extreme x squared values. We put our 5% most extreme x squared values in the upper tail there, and we call that our region of rejection. Because if we simulate from a population in which the null hypothesis hold, only 5% of x squared values will be in this region of rejection. That is what the hypothesis test is really doing. So we can also calculate what proportion of x squared values are more extreme than the one we found. And that is the definition of a p-value. The p-value is the probability of your test statistic or more extreme. So what proportion of those 20,000 x squared values was larger than 0.061? And that's exactly what we calculate here. You can again just look at my prompts and look at the code, and we can see it's about 0.707. So the p-value in our simulation here was 0.707. That's again larger than 0.05, and again we failed to reject the null hypothesis. Because we are saying about 71% of those 20,000 x squared statistics were more than 0.061. That is our simulated p-value. And what I've done here, again, I'll pause there for you to read the prompt. I'll pause for you to there so that you can pause and read the code. And there's our data visualization. Let me just run that to be sure. There we go. Look at now how I can use my simulation to understand the statistical test, because there is a version of all my simulated x squared values, and this orange line, well, that's the model I'm using. The chi-square statistic on a single degree of freedom, that is a curve. That curve is created by the PDF, the probability density function, which, remember, like at school, y equals x squared, that gives you the parabola as a curve. I have a function called the PDF, and that generates this orange line for me. Look at it. It also has an area under the curve of 1. Remember from a density histogram, look at my videos on that. A density histogram, if you take the width times the height, you get the probability of an x squared value on that bin. If we look at it closely, it seems to go from, let's have a look, a bin width of 0.5, because we go from 0 to 0.5, 0.5 to 1, 1 to 1.5, and 1.5 to 2. So if I want to see what proportion of x squared values were between 0 and 0.5, I would take the bin width, that's 0.5 times the height. That gives me the probability, which means if I add the geometric area of all of these little rectangles, it's going to sum to 1, meaning the probability that x squared falls from 0 all the way to infinity is 1, or 100%. The x squared clearly must fall somewhere, and that's what my model is also doing. I can look at the area under the curve, it is 1, and any proportion of it on any interval will tell me the probability of finding a value in that interval. And that's exactly what I do with an Xcode. I'm going to calculate a critical value. I want a value for this model, the chi-squared distribution, such that only 5% of values will be greater than that value. And look at that, it turns out to be 3.841, which is very close to our simulated value, which was 3.4. Now remember, we only simulated 20,000 cases, so yes, we're not going to get exactly 3.84, but we're getting very close. And what we are saying, the probability that x squared is greater than 3.841 is 0.05. Therefore, 0.841, that is our critical value. And again, I'm going to visualize that. I'll pause here. You can pause and read my prompt. Again, for the code, a little bit more for the code. And this is what we see. In the end, this is what we see. I've taken away my simulation now. Here's my chi-squared distribution, the PDF, drawing that curve for me. I can see right there at that orange line, that's my critical value, 3.841. And I'm saying is, in this distribution, only 5% of values will be larger than 3.841. That is in the extreme cases there, and that's what I call my region of rejection. But now through simulation, you can see exactly where this comes from. And look at my test statistic in green here. It is not in that region of rejection. It's one of the 95% least extreme x squared values. And again, I'm going to fail to reject the null hypothesis. Let's have a look at visualizing our p-value. That's the probability of your statistic. That was 0.061 or more extreme. Look at it. There is my prompt. A bit of the code. A bit more of the code. And there's my plot. So you can clearly see what a p-value means. It's the probability of your result. There's ours, 0.061, or more extreme. So towards the upper tail there. And if I look at this green area under the curve, that is much larger than this darker orange area here. Remember, that was the 5% most extreme x squared values. So clearly this green area is a lot bigger than 5%. So the p-value is larger than 0.05. And when you see something like this, I always want for you to see in your mind's eye tiny little rectangles, behind the scenes. And what this green area is showing is, let's just sum over all the geometric area of those little green rectangles. That's what the area under the curve is representing. And here, that is 0.81. So this constitutes 81% of all x squared values will be larger than 0.061 under the null hypothesis. Once again, our region of rejection up here, those values of x squared there are completely legitimate under the null hypothesis. We're just willing to say, well, if we get one of those 5% extreme cases, we are willing to reject the null hypothesis, making a type 1 error. And there we go, simulation, or at least visualization of our p-value. So I hope this demonstration of using simulation to understand the chi-square test for association helped you out. Leave a comment. Let's discuss it in the comment section down below, and I'll think about the next video where I use simulation to help us understand a hypothesis test.